this. Okay, so it's first time. So welcome Erich Kaltofen from North Carolina State. He will talk about marriage made in heaven, symbolic and numeric computation.
Thank you very much, Alexei. I was invited to give this talk in the spring, but was teaching 2 courses in the spring, so I delayed my coming here to the fall semester, which actually is good because I'm not teaching this semester. But it's better even because the talk I'm going to give here is a talk I gave at the International Congress for Industrial and Applied Math in Beijing in August. And you get the same talk. Now I have to.
Why do you have the word hybrid then?
Yeah, I will explain this later. Hybrid constitutes the notion that the algorithm should have both numerical and exact parts in it. And you will see it on the examples I give. So this somewhat should distinguish us from simply numerical algorithms that may be done after symbolic preconditioning. These are algorithms that really should incorporate both. And I actually will give 2 examples of this. But symbolic-numeric computation has been done for a long time, so the earliest paper I know is one that explores whether one can use the Euclidean algorithm, floating point numbers, and this actually was also tried in the first implementation of Mathematica. So there is an old report that I know because I'm old enough, that was written in 1988 by my PhD advisor. I'm very glad to see you, William.
Sorry about this.
And it will be on the recording.
Yeah.
So, and there actually, this was mentioned as being one direction that has to be developed. The incorporation of floating point arithmetic into symbolic computing, and actually the report also talks about developing courses for this. I don't know whether there is a course on this anywhere today, and also to have conferences, and you will see there are plenty of conferences now on hybrid symbolic numeric computing. But this is old. So and then, of course, one tries to find a name for the discipline. And there are many names. I named the workshop Integrated Symbolic Numeric Computing in 1992. SNAP, Symbolic Numeric Algorithms for Polynomials. Then there was a project in Linz. We called it hybrid in our article in the handbook for compute algebra. That's where we first mentioned hybrid. I replaced integrated by hybrid. And today, many people use the word hybrid for their algorithms, but not in this sense. Not in the sense of combining exact and floating point arithmetic. And we have APCOA, we have, I believe, you called it approximate.
No,
algebraic
numerical. Exact numerical computation.
Oh, exact numerical computation.
That's right.
Okay. Which actually wouldn't maybe it would qualify for hybrid.
Yeah, definitely hybrid in your sense.
I somehow exclude computation that uses high precision floating point arithmetic. The floating point arithmetic should really processor-based floating point arithmetic, but of course the boundaries are not clearly defined, what I might want to say here. So hybrid, famous hybrid. So The Sphinx is a hybrid. It has a human head and the body of a lion. I have a hybrid rice plant. So there is there were these two varieties of rice in India, one of which could survive underwater for a prolonged time, for 2 weeks. But it had very low yield. And so this was hybridized recently by people at the University of California, Davis, and is revolutionary because of global warming in Bangladesh. That's what they have to plant now. And then, of course, we all know the Toyota Prius. So in my world, the floating point arithmetic, that's that white rice, the rice where the plants have lots of kernels, yields a lot, and the symbolic part of the algorithm is the algorithm that can survive underwater for a long time, so that can essentially survive a very adverse environment. And of course, for us, adversity is always to be near a singularity. So that's what we will see. And I put the two hearts. When you see a heart on my slides, that means that you either have a symbolic part or a numeric part. So here's some algorithms. So this used to be an area of a lot of investigation. Approximate GCD. Victor isn't here. He had an algorithm in 2001. Was a very active problem to be investigated, but ultimately, actually, for univariate polynomials, what is discovered is that for univariate polynomials of high degree, you always have an approximate GCD. So this is somewhat not such a good notion. Then approximate vectorization. So here, of course, I talk about factoring multivariate polynomials. Univariate polynomials over the complex numbers always factor exactly, but you have absolute irreducibility over the complex numbers. And so there it makes sense when you get a polynomial with floating point coefficients to find a nearby polynomial where you have an exact factorization. I will talk about sparse interpolation. Sparse interpolation is a problem that was first truly solved by symbolic computation algorithms. It's actually we brought the algorithms to numeric computing. So usually the numeric algorithms come to symbolic computation, but there it's in reverse. And I talk about that some more. I talk about sums of squares optimization later also. This is this new thing about using a semi-definite programming L1 norm minimization in nonlinear optimization. Linear algebra, it's a vast area where when you try to make exact statements, you can use floating point arithmetic. I named just a few results there, especially for lattice basis reduction. In lattice basis reduction, you have to compute the QR factorization. And the QR factorization has to be somehow guaranteed in order for you to know that the reduction algorithm will terminate in a polynomial number of overswap. So polynomial system solving, another vast area where the deflation methods, finding certificates for the solutions to polynomials, for isolated solutions of polynomial systems with high multiplicities, has been recently investigated, and including our chairs, the chair of the workshop at IKEA in Beijing. That's why she's listed there. Now, actually, maybe you don't know this, but the biggest application of hybrid computation is MapleSim. And what they do there is they they construct models that are given by partial differential equations for say, the Toyota Prius. And the difficulty there is that they have models for the clutch, they have models for the motor, and they want to combine these models into a large model, get huge models, hundreds of differential equations that ultimately then will be numerically solved. So there's a lot of work there in industry, not so much in academia. All right, so here is the first example of an algorithm. So this is the sums of squares optimization. I got this just before the talk in Beijing. Richard Askey asked me whether a polynomial was non-negative on non-negative values. And the way you prove this is that you construct non-negative values means that you substitute for the variables the square. And the way you prove that this polynomial is never negative is that you express it as a sum of squares of polynomials. And we did it. We have an algorithm, we call it RT-improver, that will compute the squares. And then you have a proof that the polynomial is non-negative. Now, the emphasis here is that this has to be true exactly. And the reason for this is a phenomenon that I only discovered when I was doing this proving minima of polynomial functions to be global minima by proving the polynomial inequality of all control variable values. So mu here is the infimum of a polynomial function, and what you have to prove is that f minus mu never can be negative. And the way the first property you realize is that the infimum or the minimum is a place where you are ill-posed. Because if you change that minimum infinitesimally, it's no longer a minimum. You can become negative. That's the first thing you realize, that you're looking for an ill-posed place. But what I only realized much later is that the proofs themselves are ill-posed. So this is what is well known to us in linear algebra, where when we take a matrix that is rank deficient, and we infinitesimally change some entries, we get a full rank matrix. But this is already true for the first inequality you learned in school, which is that x minus y squared is non-negative. So what happens here is if you perturb one of the coefficients, say the coefficients of, I call it here xi, to be distinguished from variables. So if you perturb the coefficient of this xi squared infinitesimally, the infimum of this function becomes minus infinity. And the reason for it is that you can plug in xi equal eta, and then you get minus epsilon eta, and if the eta is large as minus epsilon xi squared, excuse me, you make the xi as large as you want, and it becomes as negative as you want. So here you have a totally different phenomenon from the phenomenon you're familiar with rank. The rank, when you infinitesimally perturb an entry, can only go up by 1. Here, when I infinitesimally perturb a coefficient, the infimum goes from 0 to minus infinity. So we investigated this in 2010. What can I say? I gave this talk in Beijing, and Jean when I was there, speaking after me in his talk, had all these numerical sums of squares. And I told him this is meaningless because if I change the last digit of this one coefficient, maybe the infimum becomes minus infinity. You cannot argue this way. And, so this is something we are writing a paper about. We now can characterize this ill-posedness, at least if the function is the sums of squares. All right, I will talk. Are there any questions? Yeah, I should ask. Are there any questions about this? Because this is all I say about semi-definite programming.
How did he respond to your question, to your comment?
Okay, so I can tell you what he said in his talk. He said on real life problems that doesn't happen. And I told him x minus y squared is pretty real life for every high school student. So I don't believe it. I don't believe that this phenomenon does not occur in optimization problems from the practice. He said something else also. He said that actually this is okay because the numerical algorithm will simply find the inequality that is the good inequality. So it will remove that epsilon perturbation internally through STP programming. So this is a more reasonable remark. And then actually, with him I can talk about these things. He doesn't take them personal, and I think we are now aware of this problem and want to do something about it, want to explain it. All right. So, but what I will talk about more is about sparse interpolation, because this is the problem that came from, in this case actually, from Reed-Solomon error-correcting decoding. And here the problem, William is familiar with it. Maybe I give you a better answer today for your question. We want to reconstruct a sparse polynomial from values, but where we choose the values proportional to the sparsity, not the degree. And the claim, of course, is that from 2t plus 1 values, I can reconstruct both the t and the term exponents. So this is an exact problem. The exponents are integers here. And then, of course, the coefficients you find by, say, least squares fitting or something. So the underlying algorithm for this is what is called the Blahut algorithm. It's a version of Brownie's algorithm. Brownie discovered this algorithm 200 years earlier during the French Revolution, but he used it for interpolating sparse exponential sums. Harmonic functions, overlays of several sinusoid functions. And we will simply talk about the polynomial version. So the main theorem for this that makes it possible to discover the sparsity without knowing much about the sparsity is what we call the early termination theorem. So if you plug in powers, consecutive powers of a random value, omega here is the random value, and we plug in omega to the k to compute h sub k minus 1, then this Hankel matrix I've written down here that has these consecutive evaluations as rows shifted over by one position as you go down. So this matrix has equal elements on its antidiagonals. The theorem states that for a random value, you see non-singular leading principal submatrices, the matrices in the upper right corner will all be non-singular until you hit the sparsity. And by the way, I don't know whether I forgot. I have it here. Once you know the sparsity, you can compute the term locator polynomial. So you solve for these C's here. You solve the last non-singular. You solve a system for the last non-singular. That's the Levinson-Durbin equation that you solve. You get a polynomial that is guaranteed to have as its factors, as its linear factors, the values of the terms at that omega. So this is what we call the term locator polynomial. So once you have this sparsity, you solve a Hankel system, you factor a polynomial, you take logs with exponents. And I promised to give a better answer to William asked me in Beijing how one can guarantee that you have that you only find one sparse polynomials, and maybe this is a better answer. You can guarantee it not without knowing something about the degree. But what it is here, if you think about it, the probability depends on the degree divided by the size of the sample set from which you randomly poll that omega, so that omega actually, in order to have a reasonable probability to achieve the early termination property, you need as many bits in your omega as is the log of the degree. Not the degree, the log of the degree. Because if you have a log degree many bits, then you have maybe 20 times degree many elements, and then you have degree of, you know the sparsity here, it's also log of the sparsity. And I think that is something I sort of slipped in Beijing without explaining. That somehow the degree doesn't go away. It's still there, but it's hidden there. Because actually in the practice, we no longer think of it. We just choose a random element. All right, so I'm glad I got the second chance of this. All right, what's the difficulty? The difficulty is to do this with floating point values. So the H sphere, the values of that sparse polynomial are not exact. They have noise in it. And so we can, to some extent, control noise. And the way we do it is, which we call the numeric Schwarz-Sippel lemma. I always write Sippel-Schwarz. It's not in alphabetic order, so I don't know why I put Sippel first. There are other people who knew this lemma in its exact form before, and what this lemma says is, if you evaluate a non-zero polynomial at randomly selected roots of unity. Now the polynomial here has to have integer coefficients, and these are Gaussian integers. Z of I here is the square root of -1. Because I need I, because I'm going to evaluate the roots of unity. Roots of unity are complex numbers. But if you evaluate a non-zero integer polynomial, multivariate integer polynomial, at these random roots of unity, you're separated from zero. It's not just that you're not zero, you're separated from zero. And why is this useful? Because we know that the determinants here are non-zero. So say if this polynomial has integer coefficients, that sparse polynomial we are evaluating, then the determinants will not just be non-zero, they will be separated from zero. All right. This, of course, there's a mistake I made here. This is a mistake I made long in my life because I thought that was enough. This was enough. You just, when you do Blahout interpolation of sparse polynomials numerically, you're guaranteed by the early termination theorem. By the way, the signal processing people discovered this now. They use random values. They use our early termination. That you're guaranteed to have well-conditioned submatrices. And yeah, for Brownie you can explicitly estimate the condition numbers from above. So this seemed to be a time finished, but actually there is a mental mistake here. And the mental mistake is, not only do you have to identify the non-singular submatrices, the termination criterion says the first singular submatrix indicates the sparsity. All right, that's a zero polynomial. That polynomial, that's a polynomial that evaluates to zero. So you say, oh, this is easy. We just check whether we are close to zero, because we know that the non-singular matrices are separated, the determinants are separated away from zero. That was my thinking. And it has a fatal flaw. And the flaw is that the matrices we're looking at are near singular. They're ill-conditioned. Now, it is not clear. This is, of course, something that is not immediate. That the determinant of these matrices is also an ill-conditioned quantity. A quantity, ladies, there are no ladies, gentlemen, a quantity is gentlemen. The determinant, if the determinant function is ill-conditioned, then minuscule changes in those h's will move you away from zero. So you think you're in the still non-singular case and don't terminate at the sparsity. This is a fatal mistake in thinking. The question
So you mean determinant before sparsity then?
after. Because it's the zero, that value that should be zero is the value of an ill-conditioned determinant.
But I thought you said
And if you do it,
it was separated. Separated means that there is some neighborhood, in which you.
if it is non-zero, if it is zero, that's the flaw. If it is non-zero, I said
Then it's wrong.
But if it is zero, I'm dead.
And then you can go as close as you want.
Yeah.
All right.
Yeah.
But I thought that if it's zero, I mean, it's continuous, right? The determinant function is zero. So
Yeah, but it's ill-conditioned. There's a high gradient. I cannot do a floating point evaluation.
Well, yeah, I mean,
The question is, what's the condition number of the condition number? If I could estimate the condition number, if the condition number was well conditioned, I just estimate the condition number. Condition number will tell me that I have repeated a singular submatrix. And what can I say? It was a mental error in my thinking, but of course, it's, how can you not see it? The condition number can be ill-conditioned. It can be small, it can be big, or it ill-conditioned. When it's ill-conditioned, the condition number, I get a bad estimate. I'm off by a factor of 1,000. But it doesn't hurt me, because it's big already. So I will actually diagnose the ill-conditionedness of that larger matrix correctly with a bad condition number. It will stop right if I estimate the condition number, not the determinant. That's the distinction. That's what we do. We wrote a paper about this. It's a classical termination criterion now in signal processing. And the practitioners know it works. They say, well, it comes out right. But why? So, there is, of course, for G, I say this for you, G. There is, of course, one property of this hybrid algorithm. I call it a hybrid algorithm because it uses the exact early termination criterion that we gave as an exact statement, and then we convert it to a floating point algorithm by replacing the singularity test by a conditional estimate. But the reason it works, I say this for you, G, is because I never use that ill-conditioned quantity. I use it for a single reason, to terminate it. The quantity itself is never used anywhere.
Well, it's like the way we use root bounds to stop. But the root bounds are not used in the computation.
Yeah, I don't know whether you stop on an ill-conditioned quantity.
I don't. Well,
I mean, that's the point here, is that you stop on an ill-conditioned quantity where you've made a terrible estimate, but you're still okay because the condition number is largely off by a factor of 1,000. It doesn't affect it. You still think it's ill-conditioned. You don't know that. You don't know what the number actually is. That's why it works. It took me some time to make this change. You think zero, oh, if I separate the non-zero things away from zero, I'm done. Just because you believe that you can identify zero. But you can't, if it's ill-conditioned. If it's well-conditioned, you have no problem. You know you will be close to zero. All right? So everybody with me?
So when you're doing all these analysis, you actually use floating point arithmetic, or you just use real?
You compute the condition number estimates in floating point.
Yeah, but the theory, in the argument, the proofs and all that, do you actually look at the arithmetic of floating point, or just real numbers? It's like a theory.
In all honesty, what we would have to do if we were to write down a theorem, we would have to say that our floating point estimate of the condition number is within a factor of 1,000. We don't have that theorem. The reason we don't have, I go back, it's a good question. The reason we don't have it is because the explicit upper bounds, we need an explicit lower bound for determination. And then we have to say we can estimate this lower bound with floating point coefficients within, say, a factor of 1,000. And that we don't have. So how do you write the paper, right? You run a ton of examples. You put fancy tables in there and say how many times you failed to discover the sparsity. And you do it by experiment. You say the experiments fail us out.
Well, there are two things. I mean, one is because it is only a probabilistic statement anyway.
Yeah,
But that's different
So the probabilistic statement, I also tried to do the expectancy. You want to do the expectancy of the condition number. That is actually easier.
But that's all just doing by real, right? Using real analysis.
Well, the expectancy of the condition number is an exact quantity.
Ah, okay.
Well, it's again, I don't know. I don't know. Today I got the question. It's actually they're actually, when you do random matrix theory, there are actually two schools of thought. One says that you do it over the reals, it's enough. And for example, Terence Dow thinks that's not enough. You have to also prove it for the discretized version of the expectancy. So for example, the estimates on the spectrum of a matrix, of a structured matrix, he actually transferred that real result to a discretized result. That's extra work. That's another 50 pages. We did nothing. We just ran the experiment in our paper in 2011. All right, so I have 20 minutes to go. I want to talk about another problem in sparse interpolation, that in doing sparse interpolation in a different basis, in Chebyshev basis. So, and a little bit about error correction also. So, I just have this here because I gave this talk in China, and I remember when, like several years back, I had an argument with my collaborator Ling Hongxi about the Pythagorean theorem, because there is a claim, it was also in the Beijing Intelligencer, that the Pythagorean theorem was invented by Chinese mathematicians. And I don't think this is entirely supported by the community that does history and mathematics. And she got sort of angry at me. She said, how about the Chinese remainder theorem? You guys also invented this? And I said, no, the Chinese remainder theorem, that's you guys. And then actually when I studied it, I found out all of interpolation is from China. So the famous Newton divided difference method was invented how many years earlier? so that I just did because all right. But we want to interpolate with errors. And for that you have to go to America. So the Reed-Solomon algebraic error correcting code was invented in 1960 by Irving Reed and Gustav Solomon, and they didn't patent it. They should have. It's in this computer. If it has an optical drive. Your DVD player does the error correction of the compact disc using the Solomon decoding. All right, so, and I want to show a little bit about this. I can already see I have to stop in 20 minutes. So first, I show you the original Reed-Solomon decoder. So, you do interpolation. Dense, univariate, polynomial interpolation over a field. And you assume that some of the values you get are erroneous, are not the values of the polynomial. Now, you have to oversample, and the error rate in Reed-Solomon decoding, for every error you have to get another good value. So this is why you have to have d here. We are going to interpolate a polynomial of degree no more than d minus 1. So we need d values for Lagrangian interpolation. We have e errors at most. We could have fewer. We don't know how many errors we have. But for every possible error, you need another good value. And the claim is that then you can reconstruct the polynomial. You don't know which values are erroneous, you don't know how many. Now, that it is an error correcting code is easy to prove. I don't have the proof here. I took it out. I thought the proof was here. Because you have E errors. If you have two solutions, the first has E errors in some places, the second has E errors in some places, but you had oversampled by 2E. So you still have T values at which the two polynomials agree, so they must be equal. That's the proof that it's a code. I gave it in words. The strangeness about it is, once you have a code, the decoder actually can be just solving a linear system. I should say this. But the strangeness about it is that the linear time decoder was first discovered 26 years after the code was invented. And what can I say? This is our interpretation of the Welch-Burlekamp decoder. It's a patent. There's no paper published. You have to read the patent that they took out. And actually, the idea now is very clear. You don't do polynomial interpolation, but you do rational function interpolation. And you introduce what is called the error locator polynomial. This is a polynomial that at the erroneous arguments, where you got erroneous values, has a root. So what actually happens here for the interpolation problem, if you plug in the psi sub L sub 1, you get 0 over 0. The strangeness about it is you're actually interpolating a rational function that is unreduced. It's actually a polynomial. And moreover, you have evaluated at a pole. What can I say? Clement explained the proof to me 3 times. I didn't believe it the first time. I didn't believe it the second time. I believed it the third time. The proof in the textbook about Cauchy interpolation will just work. There's no assumption that the fraction has to be relatively prime. There's no assumption you cannot evaluate it at a pole. It just works. Well, if Reed Solomon had known it in 1960, they could have written the patent right there and then. All right, so we use this, because we are writing a paper about this now, right? Once you see it's like, what is this? The Welch-Burlekamp decoder is run in Maple as calling, what is it, rational function field. It's incredible. But you can, of course, generalize this, not just when you interpolate a polynomial, but when you interpolate a rational function. And when you interpolate a rational function, you can generalize it to a vector of rational functions, where you have a shared common denominator, and then something happens. What happens here is, when do you have an error? You have an error, so here you're not transmitting a single evaluation, you transmit a vector of evaluations. What is known for the engineers is that when they have an error in a transmission, they have a burst of errors. An error rarely comes alone. Errors are not distributed uniformly over the transmission. So what this will do is, if you look at that vector, when you hit a root of that error locator polynomial, you hit the root in the entire vector. So this decoder will give us a much higher error capacity when we have bursts of errors. We'll beat the Reed-Solomon one, under the assumption that there are bursts of errors. And this we are writing up. You have to prove something. You have to prove that you beat Reed-Solomon decoding, and this is done by what is called Cavay's early termination for solving a linear system. So we actually, this f over g, the vector f over g, has to be a solution to a linear system where the coefficients of polynomials in X.
When you count the errors each, you count just the value of the function, or do you also count the errors perhaps of the argument of the?
Yeah, but so either one can be erroneous. So it's an error.
So in order you count both.
Yeah, you could do it both ways, right?
But in your theory there, do you assume that the sides are correct?
At an erroneous place, it can be wrong.
Okay, you do a
right. If you have an erroneous place, you have a wrong side, but the right value, it makes no difference. Because it doesn't match the value at that erroneous argument. As soon as you don't have a matching argument value pair, you declare it an error. All right.
And you don't know F, do you? F is a black box, right?
No. Okay. So we are transmitting data, and the data we are transmitting are the coefficients of F. We are not yet doing interpolation.
Okay.
But you see, William, the interpolation step is the decoder, because it doesn't know F.
Right.
So that is the decoder.
But this is just the transmission.
Yeah, but the decoder does not know F. That's the whole point. Okay. There is the heart, right? On Pluto, sent by a high-yield 100 amp antenna from a distance, I don't know how many million miles away from Earth, with an air-affecting code, and it shows the heart, right? There's a heart there. So, how do you do it for floating point numbers? Can you do interpolation with errors using float? Is useful. It's especially useful when this function f at one argument or several argument size is ill-conditioned. It can be well-conditioned elsewhere, but if it's ill-conditioned, you don't get the value, so you remove the outlier. So how do you do this? Well, as I said before, you can always set up a structured linear system where you give the coefficients of the error locator polynomial, we call that psi, and the coefficient of the error locator polynomial times the original polynomial phi, and you solve that linear system. And this is this result actually is quite famous, Olszewski's Chocolate. This is a decoder that is numerically stable for interpolation with errors. A question here now is, why does this not become approximate GCD? So you get the lambda as the lowest degree psi, and you do an approximate division with the phi to get the f. Why is that not approximate GCD? And the answer is, this is a terrible idea. Because the lambda that you get is only an approximation of the actual error locator polynomial. Because you have noise in the data. You have noise in the place where you didn't have an error. So what to do? And the answer is, of course, but the psi you have computed has to have as its roots the arguments where the errors occur. So you just match the arguments with the roots of psi, approximately. And then you know where the errors occurred, and then you do least squares fitting on the non-erroneous. You locate the errors. You don't do an approximate division. That's what we do. That's what we discovered. So here is the heart, because this is, of course, avoiding the numerical algorithm and using a discrete algorithm to simply identify which argument is near a root of the psi. All right. We do this in the multivariate. Yeah, what can I say? We didn't write the paper for Olszewski-Szokolahi. They wrote the paper on it, but we did it for multivariate models, for rational function models. But the algorithm is essentially the same. Difficulty, so here is, maybe I should spend more time on this, because one has to realize outlier detection. If you have one outlier, if you have one place where you validated an ill-conditioned argument, no big deal. But what if a quarter of them are bad? So a high error rate affects the conditioning of the good systems. And the question is why? And the reason is because if you have an error rate of 50%, you have two solutions. You're guaranteed to have two solutions. Because you can make the errors a second solution. So, ill-conditionedness hits us at higher error rates, and so I say this. I skip over this, I don't have time. This was a consequence of the theorem we proved for how many evaluations we needed for reconstructing the model. And this was an open problem in sparse Fourier analysis. But the rules are, oversampling is good for your conditioning. A high error rate is bad for your conditioning of the good system after the errors have been located. I skip over this too. I want to talk a little bit about using a different model of sparsity, that of representing a polynomial sparsely in Chebyshev basis. So this is because of Chebfun by Nick Trevethan. That's what they use. So these Chebyshev polynomials of the first kind here are defined as the polynomials you get when you compute that matrix power. This, of course, incorporates the recurrence that you usually see. That the new Chebyshev polynomial is 2x times the previous one minus the one before it. So that's the recurrence. So this matrix equation defines the Chebyshev polynomials of the first kind for all the integers. And now we assume we have a sparse polynomial in that basis. It's not sparse in power basis. There are a few Chebyshev terms. How do you find the for second kind C-Schenkfenster? This is also from Beijing. I didn't take it out. We have a new result for second kind. So there is an algorithm like Browning. Evaluating at consecutive values you pick xi and you evaluate consecutive Chebyshev polynomials. So this is very similar to what I've shown before with power basis. You get a term locator polynomial, you factor the term locator polynomial, you get the deltas, and then you compute the C's. Yes? But what we want to do is we want to correct errors here. So he gave this example. So when you do, that's Andrew Arnold's example. This is who I did this work with, a PhD student at Waterloo. If you do Chebyshev interpolation and you don't remove the outliers, you get of course a dense polynomial, and you get a fairly poor fit. But if you identify the three outliers, you get a perfect fit. So this is the problem we try to solve. We try to find the outliers in this.
The Chebyshev interpolation is known to be pretty poor fit for, say, polynomials. Right? You have all these oscillations.
Yeah, how good a Chebyshev representation is for a dense polynomial, I don't know what the numerical properties there are. I'm only dealing with sparse polynomials. Maybe for sparse polynomials you're right. Okay, so I have 2 minutes left, and of course I have way too much to talk about. But a first error correction algorithm could just be a simple block code. So, because we know that with Lakshman and Saunders, if we get one row of these evaluations without error, we can reconstruct the polynomial. So you just evaluate the polynomial at different places. In blocks of 2t, if you get one without an error, you have the polynomial. And this is what is called it gives. If you have e errors, you need e plus 1 times 2t evaluations. And one can prove by the Carr rule of sign for sparse Chebyshev polynomials that there is a unique solution. There is no second solution. So here I stated the Carr rule of sign. I'm going to skip over this. So we want to do better. We want to do better than e plus 1 times 2t. And our result there does subsampling in the indices are subsampled at arbitrary arithmetic progression, and we actually can prove that for certain term counts, for example, for 3 terms, you beat the previous one. You beat the 6e plus 1. So the actual number of values we need with our new algorithm is lower than that. The problem is, one knows, because of this Carr rule of sign, that you actually only should need 2t plus 2e evaluations. And for that, we have no polynomial time decoder. So here, the polynomial time decoder has many more evaluations, but can decode in polynomial time. And when you have very few evaluations, you have to spend triple exponential time to decode. And hopefully, eventually, we find a polynomial time decoder for this. So, this concludes my talk. The marriage made in heaven. The singularities are places where numerics fail. But they're actually the places where symbolic algorithms excel, because they don't care whether you have a rank-deficient matrix, they just compute the rank. So these singular places, that's the rice underwater. But the singularity is actually often where the action is. This is what you are after. And the example, of course, I gave 2 examples. I gave an example, the sums of squares proofs. And I gave an example where the error location is a pole in that rational function in triple. So the question is, are wedding bells ringing? I don't know. I don't think I have managed in all my attempts to convince numerical analysts that they should think hybrid. I think numerical, but I don't think the they see a value, for example, in trying to do something at a singularity. Thank you very much.
More questions, comments?
T is the number of terms.
Yes.
So in the interpolation,